Hello everyone. In this lecture I shall discuss the Newton-Raphson method to solve the algebraic and transcendental equations. As I have told you, in our previous lecture I have discussed the bisection method, the regular falsi method, the secant method. In comparison to the all other methods, the Newton-Raphson will rapidly approach the root. Okay, so this Newton-Raphson method, in short we write it NR method. Also it is sometimes called simply the Newton's method, right? It is one of the most widely used numerical methods for evaluation of, you mark the word, simple root. Okay, simple root, say alpha, right? Not repeated, right? Once the root is repeated, then the convergence is slow, right? Simple root of the equation fx is equal to 0. Now suppose you are given an equation fx is equal to 0 and x0 be an approximate root. How to know that x0 is an approximate root? By using the intermediate value property, right? fa into fb negative, and you find x0 in fb. So how to get it? You get it fa into fv negative, right? And x0 belongs to your ab. So you find the x0 be an approximate root of the equation, right? Initially approximate you can get it by using the mean value, intermediate value property. So now this x0 is an approximate value. It is not exact. To make it exact, suppose we need a correction. We need, suppose this is the correction. With adding h, this h is my error here. Okay, so with this correction, this becomes the exact root now. Okay, so now in view of deriving the formula, we try to find h such that f dash x0 plus h is equal to 0. Means this is the exact root. So at this point, the function will 0. Okay, in that way, we will interpret to get the derive the formula of Newton-Raphson method. So before deriving the details formula, let me to introduce myself. Myself, Professor Sushant Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra Sai University of Technology, Burla, Odisha. So without much delay, let us now start the detailed discussion of this NR method. Derive the formula for NR method. Okay, recalling your Taylor series expansion. Recalling the Taylor series expansion. You know f of x0 plus h is given by f of x0 plus h f dash x0 plus h square by factorial 2 f double dot x0, so on, isn't it? So in this context, we have f of x0 plus h is equal to 0. So this is equal to my 0, say here. Okay. So now this h is very small. H is error quantity is very small. So h square h cube, right? Here h square h cube, as h is small, h is small. So h square h cube are very small, very small, very small, and close to 0, and close to your 0. Okay, so you can omit them. We can omit the higher terms, right? So this implies so this will lead you to your fx0 plus h f dash x0 is equal to your 0. So what is my h? If you simplify it, your h will be your minus of f of x0 divided by f dash x0. So as we are interested in, we try to find h, right? We try to find h, so we get the value of h now, right? So coming to the first approximation, let the first approximation be x1 is x0 plus h. Coming to the first approximation, right? You say x1 is my x0 plus h, right? Then what is your x1? x1 will be your x0 minus fx0 by f dash x0, right? this is my x1, provided the denominator f dash x0 is not equal to 0. Likewise, talking about the second approximation, right? So here you just replace x0 by x1 and x1 by x2, right? Then what you will get? You get here x2 will be x1 minus fx1 by f dash x1, okay, provided f dash x1 is not equal to 0, the denominator is not equal to 0. If you go on continue, here n plus 1th approximation will be x n plus 1 is equal to xn minus fxn divided by f dash xn, okay, and here f dash xn is not equal to 0, and here n is here 0, 1, 2, so on, okay. So this is my necessary formula with this is the restrictions, okay. The denominator is not equal to 0. Putting n0 will get x1, putting n1 will get x2. So this is the generalization of this formula. Now to understand its geometrical interpretation, let us see the diagram. Coming to the geometrical interpretation, you consider the curve, given curve y is equal to fx in xy plane, okay. Suppose this is my curve y is equal to fx. Y is equal to fx is my given curve, right? So we consider the curve y is equal to fx is my curve here, right? Now this curve cuts x-axis at say alpha, so alpha is our desired root. Now we have an initial approximation. Let x0 be my initial approximation, x0 by initial. The corresponding point on the curve is my x0, f0, it is f0 or fx0. This is the corresponding point on this curve. So now at this point I draw a tangent line here, okay. I draw a tangent to the curve at this point, right? I draw a tangent. So now, as I have told you, so we draw a tangent at the point, at this point here x0 on this curve. Now suppose this meets the curve, so x0 is my initial approximation, right? x0 is my initial approximation. Suppose it meets the curve at x1. So now the corresponding point on the curve here is, this is my x1 f1 is the corresponding point on my curve. x1 f1 is my corresponding point on the curve. So now at this point again I draw a tangent, right? At this point I again draw a tangent, right? So now this cross x-axis at here, say at here x2, right? At here x2. So this at here x2, this is your x2 point, right? This point is your x2. So my initial approximation was x0. Subsequently my next approximation was x1, and I get my next approximation is x2, and I go on make it close to the original root here alpha, okay. So geometrically we will able to write it in this way. We will able to write it, you see. So the equation of the tangent, right, at x0 f0, the equation of tangent, let fx is equal to 0 be given curve, right? Equation of tangent at x0 y0 f0 is here y minus f0 is f dash x0 into x minus x0, right? But this point is my, you say p, this point is my p, x10, is not it? So at p x10, right, this tangent meet meets x-axis, means here y is equal to 0. What does it mean? It means here y is equal to 0, right? So here minus f of 0 is f dash x0 into x minus x0, right? So this implies, sorry, so this point is my x1 na. So now this is my x1. So what is my x1 now? So that means minus of fx0 divided by f dash x0 is equal to here x1 minus x0. So now what is your x1? So this implies here x1 is equal to, bringing this to this side, x0 minus fx0 divided by f dash x0. Okay, so is it not our first approximation? Is it not our first approximation? Right? So this is our first approximation as we did it here, here, right? So likewise we can extend it to get the general formula. Okay, subsequently for x2 and so on we continue it to get the general formula. Xn plus 1 is equal to xn minus fxn by f dash xn. So this is the geometrical interpretation of your Newton-Raphson method, right? So here y is 0 means I can write it 0 minus this. Okay. So coming to the remark, one important observation. So this is the necessary formula for your second Newton-Raphson method, and this is the necessary formula for your second method, right? Now you see, if you closely compare these two, right, this factor here, this term here is nothing but 1 by f dash x, 1 by f dash x, isn't it? So what is my f dash xn? So what is my f dash xn? This is xn. What is my f dash xn? You see, my f dash xn will be fxn minus fxn minus 1 divided by xn minus 1. So f dash xn, as xn tends to xn minus 1, is it not the formula from the first principle? Right? So that means this xn and xn minus 1 are very close. So in view of comparing the second method and your NR method, we know from the derivative first principle formula, right? F dash xn is this, is not it? Is it not your first derivative formula? F dash x is limit h tends to 0 f of x plus h minus fx by h, or equivalently limit x tends to x0 fx0 f minus fx by x minus x0. Is it not like that? Right, fx minus fx0, right? So in that way, so is it not the formula for the first derivative, right? So that's why this means when this denominator is tends to 0, means these 2 points are very closer. When your xn and xn minus 1, okay, xn minus 1 are very close, then xn plus 1, the subsequent approximation obtained by NR method, is almost same as the second method. However, the NR method is quite rapid because the rate of convergence is quadratic in NR method. Wherever in second method the rate of convergence is what? In second method the rate of convergence is 1.628. Okay, so this is faster rate of convergence. However, the root should be simple, right? That means in second method, joining the second or the chord here is same thing as the tangent at this point, right? So next, in view of the remark 2, we got here h is this, right? So for interested learner I am telling this thing. Now this is my h. Now the moment this f dash x is tends to 0 is very small, right? The moment here f dash x is very small, means it tends to 0, then h is large enough, then this method is not applicable. In the nearer to the root alpha, right, then h is very large. If h is very large, then your Taylor's methods cannot be applied here and the root cannot be calculated, right? And if it is complicated to find the derivative, right, then also this method is not applicable, right? So in such case we use the secant method. If the derivative is complicated, if the denominator is almost tends to 0, then we use the secant method, right? However, NR method is more rapid, clear? Consequently, that means if NR method is applicable, then fine, we should apply the NR method. Consequently, NR method is useful in cases of large values of f dash x, right? That means mostly when the graph of fx crossing x-axis is almost vertical, means this, if this crosses almost vertical, this point, okay, is almost vertical, right, is almost vertical, right? So next, if the root is a multiple root, right, if the root is a multiple root, right, if we repeated root, then this in case of repeated root, the convergence of NR method is linear here. So linear means the convergence is 1 here, right? It is quite slow then, right? Now together with this repeated root, or the case when the denominator 0 f dash x 0, or these complicated cases of finding the derivative, right? So these are the disadvantage, I can say the disadvantage or the drawback or the pitfalls, right? Drawbacks or the pitfalls of NR method. Sometimes these such questions are asked, the drawbacks of NR method, right? Moreover, this slow convergence can be overcome by using a generalized formula. Means if your root alpha is repeated m times, then we modify the formula like this, just one m is multiplied here, okay? So this is the case of your NR method, the important remarks of this. Now let me to describe the working rule and followed by 2 examples. Coming to the working rule, so as I discussed before, this NR, the geometrical interpretations and the remarks are for deep learning. Now for simply to apply the NR method, we have the following working rule. So you consider the function, consider the given equation f of x is equal to 0, right? Let fa into fb negative. So that means root lies between a and b. Let x0 be a point, x0 belongs to ab, be my initial approximation, be the initial approximation, right? Initial approximations. So it is always necessary, so right, it is always necessary to get the initial approximation, right? Then my necessary formula is xn plus 1 is my xn minus fxn by f dash xn, right? F dash xn, where n equal to 0, 1, 2 and so on. So now if I put n is equal to 0, for n is equal to 0, right, for n is equal to 0, my x1 will be x0 minus fx0 by f dash x0, right? For n is equal to my 2, x2 will be x1 minus fx1 by f dash x1. That means you see here, we need to find out fx and we need to find f dash x, right? So this calculation, 2 phases of calculation, 2 functional value we need, right? However, what we can do, just we can simplify it, right? Just we can simplify it and express as a single function. So here my xn plus 1 will be xn into f dash xn, right, minus fxn divided by f dash xn, right, f dash xn, and I just keep it in the memory of the calculator. Keep this formula, right, keep this in calculator memory, or save this, okay, save in memory of calculator, right, for easy calculation, okay? Then subsequently substitute, put x is equal to 0, 1, 2, so on to get my x1, x2, x3, like that. Okay, x4, suppose my this is 2.735426 See, this is suppose my 2.347692. This is my 2.347864, right? So now you see here, so we are getting the accuracy. It is repeated up to 3 decimal places. 347 is repeated, so we will close it here. So I say this x4, the root is x4 is my 2.347, correct up to 3 decimal places. Okay, so in that way, this is the working rule. Means simply you just write the formula. You first find the initial approximation by mean value property, intermediate value property, apply the formula, and just you simplify the formula in this way, and you go on substitute x0, 1, 2, and subsequently find the approximations, improving approximations, and where the answers in 2 consecutive stages are nearly equal up to the desired accuracy, then we'll stop over here. So let us discuss some important examples. Suppose you are asked to solve one example. Evaluate root 12 correct to 4 decimal places by using Newton's iterative method. Newton-Raphson method is an iterative method, okay, or NR method or Newton's method. So here, coming to the solution. So you are asked to find root over of 12, right? So let x is equal to root over of 12. So that means x square minus 12 is equal to 0. So let fx is my x square minus 12, right? Fx is my x square minus 12. So now find the initial approximation. Now what is my f of 3? F of 3 is my 9 minus 12 is minus 3 negative. What is my f of 4? F of 4 is my 16 minus 12 is my 4, which is positive, right? So since I get consecutively negative and positive, as f of 3 into f of 4 is negative, so root lies in 3, 4, right? I take any value in between this. I take any value. I may take 3, I may take 4, or I may take any intermediate value, right? Let my x0 is my suppose I take the midpoint 3.5 be the initial approximation, right? Next, what is my f dash x? My f dash x is, so this implies my f dash x, because I need in the formula f dash x is my 2x. So now coming to the necessary formula. The necessary formula for NR method is xn plus 1 is equal to xn minus fxn divided by f dash xn, right? So I should substitute these values now. What is xn? My fxn is xn square minus 12. fx is x square minus 12, so xn square, it is my 2xn square. Okay, so I just simplify it. So this is equal to, if I simplify it, then it is quite easy to save in the memory. It is 2xn cube minus xn square plus 12 by 2xn square. Sorry, the derivative is 2xn here. The derivative is 2xn here, sorry. So this is square, okay. So this is square, because f dash x is 2x. So f dash xn is 2xn, okay. So now, so this is equal to here xn square plus 12 by 2xn, okay. Or I will keep it in the memory of the, so I will just keep it xn square plus 12 divided by 2xn. So I should save in the memory of my computer, memory of my calculator, x square plus 12 divided by slash 2x. So I just I save this in the memory of my calculator, okay. Just you save in calculator memory, okay, and you go on improve by putting, right, and here go on improve by putting n is equal to 0, 1, 2. Right, if you save x0 here, you get x1. Then if you save x1, then you get x2, and subsequently you go on improve. However, we may start it from here, but at each step we have to calculate. We cannot save it because the value is going to be changed for the value of x0 and x1. Right, so once we save it, then it will work for all values here. Right, so now coming to my first approximation. Coming to my first approximation. Now coming to the solution, let here f of x is x log x to base 10 minus 1.2. So what is here f of 1? F of 1 is here minus 1.2 is negative. So if you find f of 2, if you substitute it, it will be 0.59794 is your negative. What is your f of 3? F of 3 will be 0.23136. It is your positive. We see this consecutive positive and negative. So as f of 2 into f of 3 is negative, so root lies in 2, 3. Right. Let I take x0. X0 is my, suppose I am taking x0 is 2 here. Suppose I am taking x0. I can take any value. I can take 2. I can take 3. I can take any value in between them. x0 is equal to 2. Right. x0 is equal to 2. Suppose I am taking. Let x0 is equal to 2 be the initial approximation. If I take 3 also, it is close to 0. The 3 will be fine then. Okay. Suppose I am taking 2. So now I need f dash x. Right. What is my f dash x? So you must be knowing the derivative of d by dx of log x2 base a is 1 by x ln a. So this is the case. Okay, this is the formula here. So I differentiate it, the product formula. First derivative of second, so derivative of x is 1, it is log x2 base 10 plus here log, now x remains silent. Now the derivative of log x2 base 10, so 1 by x log ln 10, okay, ln 10. So now this x and x cancelled, right? So this is log x2 base 10, and if I find the value 1 by log 10, 1 by ln 10, so this will be my log x2 base 10, and my this value will be, now suppose I am taking up to 5 decimal places. Okay, you should take this complete value as per your permissible in your calculator. Now the necessary formula for NR method is xn plus 1 is equal to xn minus fxn by f dash xn. Okay, so just you simplify this formula, or step by step you start from here, n is equal to 0, 1, 2, but it will lengthy, but it is better you should simplify the formula. It is xn, and here fxn will be xn log xn 2 base 10 minus 1.2, this divided by your f dash xn, we get it, f dash xn, it is log xn 2 base 10 plus 0.43429. If you simplify it, you will get it. So this will be equal to, so this is the formula, and you can save it in the memory of your calculator, this by this, and you save it. Okay, in this way you can save it. Now my first approximation for n is equal to my 0, x1 will be 0.43429 x0 plus 1.2 divided by log 10 base here x0 plus 0.43429, right? Now what is my x0? X0 I have taken 2. Now substituting x0 is equal to 2, this will give me 2.81. Now my second approximation, my n is equal to 1, here x2 will be 0.43429 x1 plus 1.2 divided by log base 10 x1 plus 0.43429. So substituting x1 here, this value will be giving me 2.741. If I go on continue, my third approximation will be similarly, my x3 will be is equal to 2.74064. Now my x4 will be subsequently 2.74065. Then my x5 will be subsequently fourth approximation, then my fifth approximation. So this will be 2.74065. You see, it is almost same. Okay, we need up to 5 digit accuracy. So up to 5 digit accuracy, you see, up to 5 digit accuracy, it is same here. Okay, so this is my value. Hence the required root is 2.74065, correct up to 5 decimal places. You may have some extra digit here, don't issue, no issue. So up to 5 digit we need the repetition. Now coming to the summary of our discussion, Newton-Raphson method is a most efficient method because it quickly approaches the root. But the most important thing is that we have to judiciously take the initial approximation. Okay, if we will not take the initial approximation correctly, then it will quite delayed. Okay, so to get the initial approximation, we have the intermediate value property is fine. Then some additional condition is there. While I teach the rate of convergence, I will tell the conditions to take the how judiciously we can take the initial approximation. Okay, so now your Newton-Raphson method is rapid in the sense that its rate of convergence is 2, whereas the second method rate of convergence is 1.62. Right, moment when fx is very complicated to differentiate, or your denominator f dash x is approximately approaching to 0, right? Then we will apply the second method rather than applying the Newton-Raphson method. Moreover, if the root is a multiple root, repeated root, suppose alpha is equal to 2, 2, 2, it is repeated 3 times, so multiple root. So if it is a multiple root, then the Newton-Raphson method, the rate of convergence is slow, it is linear 1. Okay, so in that case we can use the second method, or we can use the generalized method. So with this, before conclude, I have one appeal to you, that if you feel that this lecture is interesting and helpful for you, please subscribe to this channel. Also like this channel, which will boost my motivation to upload subsequent lecture for your benefits. With this, let us now close this lecture. So thank you all. Have a nice day.